All right, welcome. This should be our probably first video where we talk about using area models. We are going to do this for multiplication. Area is a common representation of multiplication you learn early in grade school to represent what multiplication is good for. This, obviously, we've got polynomials here, so this is a little bit beyond our grade school examples. But we're going to jump in here and take a look at how we could use an area model to multiply these things together. So I'm going to draw my rectangle, but we're going to, and on one side of the rectangle we have 2x squared minus 3x plus 5, and on the other side of the rectangle we will put our x cubed minus 3x squared plus 2x. I'm going to throw an extra space down here. Pay attention to how big I had made that. It doesn't matter which one goes in which direction, but we are going to break this thing up then so that we've got spaces for each of those. So we have a trinomial on the top and a quadrinomial on the left-hand side. 3 times 4, there's 12 squares to fill in. I like this method because the only way that you forget to do something is to leave a square blank, and you're probably not going to do that. So now, instead of looking at this as one big problem, we have 12 small problems, and here we've got a rectangle that's 2x squared wide and x cubed tall. We kind of have to give away our thought process about what area really means here, but that becomes a 2x to the 5th. The x cubed tall, negative 3x wide, that's a negative 3x to the 4th. This one is x cubed tall and 5 wide, that's 5x cubed. Okay, no problem. Move on to our next one, negative 3x squared tall, 2x squared wide, that looks like a negative 6x to the 4th. This one then becomes a 9x cubed. We have a negative 15x squared there. 2 times 2 is 4. X cubed times x is x cubed. Negative 6x squared. Positive 10x. 14x squared. Negative 21x. And a positive 35. Okay, so these are all the pieces. This big area can be represented as a sum of these 12 small areas, which we're going to do, but we also want to make note of, we want to write this in its standard form, and so we look for the largest power of x, and as we have done this, where there are no missing powers of x in any of our polynomials, and they're all written in the standard order of largest descending order of powers. And when we do that, the biggest power is always going to end up in the top left-hand corner here. So we'll bring this all together. We have a 2x to the 5th. The next thing we'd be looking for was an x to the 4th power, and we see that those x to the 4th powers, because of the way that we set this up, are on a common diagonal. So when we add those together, the negative 6 and the negative 3, we get negative 9x to the 4th. The cubes are also on a common diagonal. Okay, so 4 plus 9 plus 5 is 18, x cubed. The x squareds are on this common diagonal. So 14 minus 15 is negative 1, minus 6 looks like a minus 7x squared. Didn't quite leave myself enough room to write this all on one line, but we'll remedy that. I'll move it all to the bottom here. I'll try to move it all to the bottom here. Okay, we've got it on the bottom there now, so we have space. The x to the first powers are all together. 10 minus 21 is minus 11x. And then we have the plus 35. The constant term is all by itself in the lower right-hand corner. Okay. There's a lot of implications of interesting things that happen here, but all we're here for now is multiplying polynomials. And so that is what it looks like. And there's our final answer. It doesn't take up too terribly much space, and I'm confident that I got all the pieces on this as well. So I am just going to do the one example of that, but and there it is. See you next time.